Okay guys, in this video we are going to be talking about gaseous mixtures and also chemical reactions involving gases. And so this first topic, collecting gas over water, this is a common way to collect the gas from a chemical reaction. So you have some sort of reaction that's producing a gas. The gas is then collected through water, so the product gas will bubble up through this water. You can collect the gas in this inverted flask, and then you can measure its volume. However, because the gas has filtered through the water, the gas will also contain, the sample here will also contain water vapor. So it won't be pure product gas. It's going to be a mixture of the product plus water vapor. Now, the partial pressure of the water vapor in the gaseous mixture is going to be related to the temperature of the gas. Okay, and so what we're talking about here is what's called the vapor pressure of the liquid. So the vapor pressure of the liquid water refers to the pressure of the vapor of that liquid that's above the liquid when it's in equilibrium with its vapor. Okay, that depends upon temperature and the type of liquid that you're talking about. And so here's the vapor pressure curve for liquid water. At low temperatures, the vapor pressure of water vapor above the liquid water is very low. But as you increase the temperature, you see that the vapor pressure, that is the pressure that you would find above the liquid, increases with temperature. And once you get up to the boiling point, that's where the vapor pressure of the liquid equals atmospheric pressure, and it's right at that point that the liquid starts to boil. So we'll talk more about vapor pressures in the next chapter when we discuss phase transitions, but for right now we need to take into account that whenever we collect a gas through water, that we don't have a pure gas, we have a mixture of that gas and water vapor. So we're going to have to make correction factors for the fact that we have a gas mixture. And so let's see what these types of problems look like. So here we've got some argon gas. 0.2 liters of argon has been collected over water at a temperature of 26 degrees Celsius and a pressure of 750 torrs. What is the partial pressure of the argon? And so we want to take into account the fact that we've got both argon and water vapor in this gaseous mixture. The total pressure of the mixture, P total, is given to us. It's 750 torrs. And if you look up the vapor pressure of water at this temperature, you'll find that it's 25.2 torrs. So this total, the 750 torrs, is the partial pressure of the argon plus the partial pressure of the water. And so to get the partial pressure of the argon, we're going to take the 750 torrs and we're going to subtract off the 25.26 torrs for the water vapor. And I'm getting 724.8. So we'll round that up to 725 torrs. So that's the partial pressure of the argon in that mixture. Here we have another problem. So we've got a sample of oxygen that's collected over water. The temperature is 29 degrees Celsius, and the total pressure is 764 torrs. We've got a total volume of 0.560 liters. What volume would the dry oxygen have under the same conditions of temperature and pressure? So if this weren't a mixture, what would be the volume under these conditions of temperature and pressure? So we need to figure out how much oxygen that we have in this mixture. So let's take the partial pressure. Let's take the total pressure. P total is 764 torr, and that's equal to the pressure of the oxygen plus the pressure of the water vapor, just like we had in the first problem. And so now let's calculate the partial pressure of the O2. So that's the 764 torr minus the 30 torrs for the water vapor. So 734 torrs, that's what we have. And now what we can do is use the ideal gas law to figure out how many moles of oxygen we have. So we'll say that the partial pressure of the O2 times the volume is the number of moles of O2 times R times T. And so we'll solve for the number of moles of O2. We need to convert our 734 torrs to atmospheres. And so one atmosphere has 760 torrs in it. Recall that a torr is equivalent to a millimeter of mercury. So 0.965 ATMs. So that's our partial pressure. The volume is 0.560 liters. Divide by the gas constant. And our temperature, 29. We need to add 273 to that. 302. .0218 moles. 0.0218 moles is what we get from that. So now we know the number of moles. And so next we want to do another ideal gas calculation where we find the volume of gas if the temperature and pressure were the same. So this time we're going to find the volume, nRT over P, using this number of moles of gas, 0.0218 moles, times the gas constant, and then the temperature again is 302, and we'll divide by that total pressure of, we need to actually convert this pressure, this 764 pressure, I'll just take it right here, 764 torrs, and we'll convert that to ATMs. And that'll give us the volume that they wanted us to calculate. So I'm getting a volume 0.538 liters. Okay, so it's not that much different than what we got with the water mixture, but it is different. Let's look at another concept here. Okay, the law of combining volumes. And so this is for what we're getting at here is stoichiometric problems involving gaseous reactions. So at fixed temperature and pressure, volumes of gaseous reactants combine in ratios of small whole numbers, just like the moles do. This is based on Avogadro's law. And for gaseous reactions, in addition to interpreting stoichiometric coefficients in terms of molecules or moles, we can also interpret them in terms of volumes. Okay, so consider this chemical equation down below. 1 mole of nitrogen plus 3 moles of hydrogen gives you 2 moles of ammonia. You could also look at this in terms of molecules. For every molecule of N2 that reacts, 3 molecules of H2 will react, and you'll get 2 molecules of ammonia. You can now do the same thing, but in terms of volumes. So 1 volume equivalent of nitrogen reacts is going to consume 3 volumes of hydrogen, and you're going to get 2 volumes of ammonia out of that. So gaseous reactions the stoichiometric coefficients can also be interpreted at the volume level. And so here we're going to be doing some stoichiometry. So we've got propane gas. It burns with oxygen to produce carbon dioxide and water. What volume of O2 measured at 25 degrees Celsius and 760 torr is required to react with 2.7 liters of propane measured under the same conditions of temperature and pressure? Assume that the propane undergoes a complete combustion. So what I'm going to set up here is the combustion reaction for a hydrocarbon. So they actually want us to figure out what the reaction is and to balance it. And so here's the combustion reaction. So we've got a hydrocarbon. To combust means that you react with O2 gas. And for hydrocarbons, when they completely combust, you're going to get CO2 gas and liquid water, at least under standard conditions and 298 Kelvin. So we need to balance this guy. So notice all of the carbon goes into the CO2. So if you've got 3 carbons here, you're going to need 3 CO2s. All of the hydrogens wind up in the water. So if you've got 8 here, you're going to need 4 there. And now what you want to do to balance the oxygens is to put something here in this coefficient. So we've got 6 oxygens here plus 4 here for a total of 10. So that means we need 5 oxygens there. So that's how you balance the combustion reaction for a hydrocarbon. You start with CO2, so balance at the CO2 coefficient, then balance at the hydrogen coefficient, and then balance at the oxygen coefficient. Anyway, so this is the balanced combustion reaction for propane. They are giving us a volume of propane. So we are to convert from liters of propane. Ultimately, they want liters of oxygen. Okay, and so we can use the stoichiometric coefficients to directly convert from liters of propane to liters of O2. As long as pressure and temperature are fixed, we can do that. So if we've got 2.7 liters of propane, we can then say, all right, for every 1 liter of propane that combusts, we are going to need 5 liters of O2. And so we'll take 2.7 times 5, 13.5 liters of O2. Okay. So this is an example of using the stoichiometric coefficients for a gaseous reaction at the volume level. Here we have a chemical reaction. I think this is my favorite chemical reaction in the whole of general chemistry. You've got, this is the airbag chemical reaction. So you have this compound sodium azide, okay, and iron 3 oxide, okay, both solids. Okay, you hit them with a spark, okay, it produces sodium oxide and some iron, and then this is where the airbag gets its punch. Out pops 9 moles of gas. Okay, so you've got some solids, and then bam, 9 moles of gas are suddenly produced. So here we're being asked to do some stoichiometry. They want us to say, how many grams of sodium azide do we need if we want to fill a 75-liter airbag full of nitrogen at room temperature and a pressure that's slightly lower than atmospheric pressure? Okay, so given the dimensions and the conditions of the airbag that we want to deploy, how much of this reactant do we need? So we're going to convert from, let's call it liters. We're going to convert from liters of N2 to moles of N2. Once we're at the mole level, we can use the stoichiometric coefficients to convert to moles of the sodium azide solid. And then from there, we can calculate the grams of the sodium azide that we need. Okay? Now, we already know how to do this part. This is just ordinary stoichiometry. We need the stoichiometric coefficients. We need the molar mass of sodium azide. Here, this is going to involve a gas law problem, converting from liters of gas to moles of gas, right? So you've got the ideal gas law, PV equals nRT. The number of moles of gas, that's what we want, is going to be equal to P times V over RT. And so you can imagine you're going to take the volume and you're going to multiply by this conversion factor, pressure divided by R times T. And that's going to convert the volume to the moles. While we're at it, let's just go ahead and get the molar mass of the sodium azide. I think sodium is 23 plus 3 times 14. We'll call it at 65.0 grams per mole. Just kind of estimated it, but that's close enough. So let's take our volume of gas. So we've got 75 liters of nitrogen. And now let's convert that nitrogen to moles of nitrogen. So our pressure, we want to do 748 divided by 760. Okay, that's going to give us the pressure in ATMs. And then we're going to divide that by 0.0821 liter atmospheres mole Kelvin. And we need to get rid of the kelvins. And so we're going to multiply that by 298 Kelvin. Okay, so this factor is going to convert this volume to moles of nitrogen. Then we can use the stoichiometric coefficients. We say, okay, we're going to need 6 moles of sodium azide for every 9 moles of nitrogen that we want to produce. And then to get the grams of sodium azide, we multiply by the 65 grams per mole. And that's going to give us the answer in grams. So I'm going to run these numbers through our calculator, 75, 748. $131 grams is what I'm getting. Okay, so we've just solved a cool problem, a practical problem. You know, given that you want to make an airbag with these conditions, how much of this reactant do you need in order to do that? And so that's our answer there. Here we've got another of these gas stoichiometry problems. So I'm going to go ahead and do this one for you just for some practice. How many liters of chlorine gas can be obtained under these conditions from 9.41 grams of hydrogen chloride? So the hydrogen chloride is our reactant, the chlorine gas is our product. This is the conversion strategy that we need to follow. We're going to go from grams of hydrogen chloride to moles of hydrogen chloride. Then we can use the stoichiometric coefficients to go to moles of chlorine, and then we'll convert the moles of chlorine using the ideal gas law to liters of chlorine. so we already know how to do this first part. We're just going to need the molar mass of HCl, right? That's going to be 36.46, I believe, grams per mole. And then for this last conversion, we're going to use the ideal gas law. We're going to have number of moles. What we want is the volume. Okay, so the volume is going to be equal to the number of moles times RT divided by the pressure. And so we can think of this as our conversion factor that we need to get from moles to the volume in liters. So let's set up the problem. We've got 9.41 grams of HCl, and we're going to divide by the molar mass. Okay, so that's going to take us from grams to moles. Now we'll use the stoichiometric coefficients. Okay, there are 5 moles of chlorine gas produced for every 16 moles of HCl that react. So now we're at moles of Cl2. And then to get to the volume of Cl2, we need to multiply by this conversion factor. So 0.0821. Got the gas constant on here. The temperature, 40 degrees Celsius. Let's convert that to Kelvin real quick. 313 Kelvin. And then we'll divide by the pressure. We've got 787 millimeters of mercury. We want to convert that to atmospheres, so we'll divide by 760. That'll give us atmospheres pressure. And so we will run this through our calculator. And so if I've done that correctly, I am getting 2.00 liters out of it. Nice round number. It must be correct, right? This one is, it's another reaction. This one is complicated by the fact that the product, the hydrogen gas, is collected over water. So this is a little bit more realistic of a stoichiometric problem. So we have this reaction between hydrochloric acid and zinc. It produces hydrogen gas. We've collected the hydrogen gas over water, and we've collected a total of 156 milliliters of that gas at 19 degrees Celsius and 769 millimeters of mercury for the total pressure. What is the mass of the hydrogen that is collected? Well, we need to first calculate the partial pressure of the hydrogen. Okay, so in this problem, the total pressure that's reported is the pressure of the hydrogen plus the pressure of the water, and so we need to calculate that pressure first. So what is that? 769 minus 16.5 for the water vapor. And we're going to go ahead and divide that by 760 to get the value in atmospheres. And so it's about 1 atmosphere, but I'm getting 0.990 ATMs. Then what we want to do is convert that pressure of hydrogen to moles of hydrogen. So taking the ideal gas equation for the hydrogen now, and we'll replace moles with grams per molar mass, and we'll solve for the little m, the mass. So it's going to be pressure times volume times the molar mass divided by RT. And we can plug in these numbers. We've got 0.990 ATMs for the pressure. Volume is 0.156 liters. Molar mass is 2.02 grams per mole. Divide that by the gas constant. And then the temperature, 19 degrees Celsius, 292 Kelvin. That's going to give us the mass that we want. I'm getting 0.013 for my answer. Okay, so in this problem where we've collected some gas over water, we have to take into account that there's water vapor in the mixture before we can calculate the amount of product that we have. Here's another problem like that where we've calculated the well, in this one it's a little bit different. They give us the mass of reactant, and then they want to know how many moles of O2 can you make from that, and then if you calculated that amount of O2 over water under these conditions, what would be the volume of the product that you measure. It's a little different, so why don't we go ahead and do that one. So this first part will involve converting from grams of potassium chlorate to moles, and then you're going to convert that to moles of O2, and that's the first number that they want. And then, given that you know the number of moles of O2 and you know the total pressure, you can calculate the partial pressure of the O2 from there. And so let's go ahead and do this in two steps. So we'll calculate the moles first. I'm going to need my periodic table very quickly. Locate that. So potassium, we've got 39.1 plus the chlorine plus 3 times 16 for the oxygen. So the molar mass of the potassium chlorate is 123 grams per mole. So starting with 1.300 grams, then we have a 3 moles of O2 for every 2 moles of potassium chlorate. So I'm getting 0.016 moles. Now they want to know if this amount of O2 were calculated at 23 degrees Celsius and a total pressure of 745 millimeters of mercury, what volume would it occupy? Now that we know the number of moles of O2, Let's calculate the pressure of the O2 that we would expect. Let's see. Yeah, let's take the P total is going to be the pressure of the O2 minus the pressure of the H2O. And so the pressure of the O2 then will be the 745 millimeters of mercury minus the 21.1 millimeters of mercury from the water vapor. And so that's 724 millimeters of mercury. And we're going to go ahead and convert that to ATMs. So I'm getting 0.953 ATMs. So now we know the pressure of the O2, we know the temperature, we know the number of moles, so we can calculate the volume. The volume will be number of moles times R times T over pressure. So we'll take that 0.016 moles, take it times the gas constant. The temperature, 23 degrees. Convert that to Kelvin, 296 K. Divide that by the pressure in units of atmospheres, 0.953 ATMs. And so we would get 0.408 liters for that amount of oxygen under these conditions. Let's see, I'm going to go ahead and stop this video here, and we'll pick up with effusion and diffusion in the next one.